Welcome back. Today, we're going to dive into a really cool mathematical puzzle. We're going to take something that at first glance looks incredibly complex, a special space of polynomials, and show how it's secretly a familiar, simple world in disguise. Okay, let's get into it and unravel this thing together.
So our story starts right here, with this specific set of mathematical objects. We're looking at a subspace of polynomials, and honestly, it looks a little weird, a little complicated. But what is it really? That's the question we're here to answer.
So here's the formal definition. We'll call this space U. Now, the really interesting thing here is that the coefficients, the numbers in front of the x's, aren't just random. They're all tangled up together. They're all controlled by just three numbers, A, B, and C. It's like they're all connected by invisible strings.
So you see that definition, and this is the natural question, right? It just looks like a jumbled mess. How in the world do you pull that apart to see what its true structure is? I mean, where do you even start?
Well, in linear algebra, whenever you want to understand a space, the first thing you do is look for its foundation. You try to find its core, its fundamental building blocks. So let's start digging and see what we find.
And you know what? The trick is surprisingly simple. We just take that big general formula and we just regroup everything. We're going to pull out the A and see what it's attached to. Then we do the same thing for B. And finally, we do it for C. It's just a little bit of algebraic shuffling.
And that's why that little trick is so powerful. By regrouping, we've basically untangled that web. We've separated out the influence of A, B, and C, and by doing that, we've exposed the core components of every single polynomial that can possibly exist in this space. And here they are, the three fundamental building blocks. Let's call them U1, U2, and U3. Get this. Any polynomial in our mysterious space U is just a combination of these three. It's just A times the first one, plus B times the second, plus C times the third. That's it. We found the basis.
And this single number, this is the key. After all that complexity, the true size, the dimension of this entire space of polynomials is just 3. It's all built from just 3 fundamental independent pieces. That's our first huge aha moment, and believe me, it changes everything.
Okay, so now that we know our space U has a dimension of 3, it kind of makes you wonder, doesn't it? Does it behave just like another, much more familiar three-dimensional space? Could we maybe build a bridge from our polynomial world to the world of three-dimensional vectors, R3?
Let's try and define that bridge. We'll call it T. It's a linear transformation, which is basically a special rule for mapping things from one space to another while keeping their structure intact. It takes any polynomial from U and turns it into a vector in R3. And notice how the parts of the vector are just simple little combos of our original A, B, and C.
But this leads to the most important question of all. Is this map a perfect translation? Does every polynomial in U get its own unique vector in R3? And does every vector over in R3 have a unique polynomial partner back in U? If the answer is yes, then it's called an isomorphism, which basically means the two spaces are structurally identical. They're the same thing in a different costume.
Right, so an isomorphism is a perfect reversible match. Nothing gets lost in translation. And here's the cool part. Because we already figured out that both of our spaces have the same dimension, 3, proving it's an isomorphism gets a whole lot easier. All we have to do is show that our map, T, is 1-to-1. That just means no two different polynomials get sent to the exact same vector. So how do we prove that? Well, we use this really clever test. We only need to check what gets sent to the 0 vector, 0, 0, 0. If the only thing that maps to 0 is the 0 polynomial itself, then our transformation has to be 1-to-1. This collection of things that gets sent to 0 has a special name, by the way. It's called the kernel.
Okay, so let's go find that kernel. We start by taking the output of our transformation, and we force it to be the 0 vector. What we get is a pretty straightforward system of 3 linear equations with 3 variables. Now, all we have to do is solve it.
And when you solve that system, it's actually pretty quick. You can subtract the second equation from the first and the third from the first. You find there's only one possible solution. All 3 of those parameters, A, B, and C, they all have to be 0.
And there you have it. The kernel of T contains only the 0 polynomial. That proves our transformation is 1-to-1. And because the dimensions match up, we can officially say T is an isomorphism. Our complicated-looking polynomial space U is, for all intents and purposes, structurally identical to the simple 3D vector space we all know and love.
So, we've built the bridge from polynomials to vectors, and we've proved it's a perfect connection.
But you know, a good bridge has to go both ways. So for the final piece of our puzzle, let's build the map that takes us back home. Because we know the map is perfect and reversible, we know an inverse transformation, T inverse, has to exist. So our goal is to find the exact formula for it. We want a machine where we can plug in any vector from R3 and have it spit out that vector's unique polynomial soulmate from our space U.
Now, the strategy for doing this is pretty clever. We don't have to solve it for every vector. We just figure out which polynomials produce the three most basic vectors in 3D space, 1, 0, 0, 0, 1, 0, and 0, 0, 1. Once we know those three, we can use a property called linearity to build the inverse map for any vector, because any vector is just a combination of those three basic ones. And after working through that strategy, boom, we get the answer. This right here is the complete formula for the inverse transformation. This elegant thing is our map back. You can literally plug in any vector ABC, and it will immediately generate the one and only polynomial in U that corresponds to.
This formula really is the ultimate solution to our whole puzzle. It's our Rosetta Stone. It confirms that these two worlds, one with these weird-looking polynomials and one with simple 3D vectors, are perfectly linked. We have a complete two-way dictionary for translating between them. We took something that seemed abstract and messy and proved it was something familiar all along.
And that leaves us with a final thought to chew on. This whole idea of an isomorphism, of finding a perfect structural map between a complex space and a simple one, it's not just a mathematical party trick. It's a fundamental tool that's used absolutely everywhere, from quantum mechanics to computer graphics. So the real question is, where else out there is a problem that just seems impossibly complex, but it's really just waiting for the right map to show us that it's something simple in disguise?